Welcome to Chapter 3, Introduction to the Atmosphere. We are going to talk about our very first sphere, which is basically a mixture of gases that surround the solid Earth. So the terms for this chapter will include atom and molecule. The reason why I bring up this atom and molecule is to help give you sort of a concrete sense of the atmosphere. Then we're going to get into our different layers of the atmosphere, various gases of the atmosphere, which include ozone, photochemical smog, and I want to note that the Coriolis effect will not be discussed until Chapter 5, even though that's in your book already. So in terms of atoms and molecules, I just want you to note a definition for a molecule. A molecule is the smallest particle of a substance that retains its chemical and physical properties, and it contains two or more atoms. So when the atmosphere starts to get a little bit more abstract, because basically you don't really see the atmosphere, it's mostly invisible, just keep in mind that we have these structures called molecules that compose the atmosphere. This is one of my favorite diagrams of the atmosphere. And this is not in your book, but I just wanted to point out that this is something that I'm going to talk about throughout these lectures. Another thing that's interesting about this diagram is that most of the weather is within 11 miles of the Earth's surface. However, based on this diagram, the atmosphere can be up to 300 miles tall. That means that much of our atmosphere does not have weather. The first way we're going to look into the atmosphere is we're going to look into it based on how the atmosphere behaves based on its composition. The first one is called the homosphere, which is the layer of the atmosphere within about 50 miles. And in this layer, gases are evenly blended. We'll talk about what those gases are more specifically in a second. The next part of our atmosphere is the heterosphere. This is 50 miles and outward. And now gases are sorted by gravity. They're not evenly blended. So the heavier gases tend to hang out at the bottom of this sphere, where the lighter gases will go up on top. I apologize if you hear mowing in the background. I'm at home trying to record my lecture. And the neighbors, of course, have to mow the grass while I'm doing this. So exactly what gases are these? Permanent gases are the ones that don't change necessarily. And you might think that oxygen actually is the #1 gas. Nitrogen constitutes over 78% of our atmosphere. Oxygen is 21%, and largely due to photosynthesis. So that leaves us about 1% left to put into the atmosphere. Argon is about 1%. It doesn't really do much to our weather and climate. In fact, in general, most of these permanent gases don't affect our weather and climate that much. The rest of the gases are considered variable gases, and they do affect our climate and our weather. Water vapor, by the way, is a greenhouse gas and has a significant effect, as you could tell just by whether or not we have rain, whether or not we have clouds. And because water vapor is a greenhouse gas, water vapor can actually warm the planet. And it is the most highly variable. It can go from 0 to 4%. Carbon dioxide constitutes a smaller amount of the atmosphere, yet it is changing, and which is why it's increasing basically, which is why we're concerned about it the most when it comes to climate change. And if you didn't know already, it's A lot of it's due to our use of fossil fuels. And then we have ozone. Ozone is found mostly in the stratosphere. And it actually is a gas that we want in the stratosphere because it helps protect the harmful ultraviolet radiation that tries to make it down to the surface of the Earth. Those are the main variable gases, even though we do have other gases in our atmosphere, other variable gases in our atmosphere. So now let's go through the various layers of the atmosphere based on how temperature behaves in that layer. And the first one is the troposphere. The troposphere is the layer that we all live in, and it's denoted by its decrease in temperatures with height. You may have noticed that because as you go up into the mountains, you will see a noticeable cooling effect. The troposphere is about 0 to 11 miles thick, and again, most of our day-to-day weather occurs in the troposphere. Going back to this diagram, you see that with this yellow line, it's showing you that temperatures normally decrease with height, up to about 11 miles. Above this layer, we have the stratosphere. Now the stratosphere, it's different than the troposphere because temperatures increase with height. Why? Because of the ozone layer. So we'll get into why that occurs in a minute. But we notice the stratosphere is around 11 to 31 miles. And the concentration of the ozone molecules tend to hang out at the bottom of the stratosphere, but its heating effect can be felt all the way up to about 31 miles, where we have the top of the stratosphere. So why does this occur? Well, ozone absorbs ultraviolet radiation, which means that less of it actually makes it down to the surface of the Earth, which is good for humans. But while it's absorbing it, it converts that energy into heat, which is why we see that warming effect in the stratosphere. Now, a problem with the ozone layer is that in some places, like over Antarctica, we're seeing a thinning of the ozone layer, mainly due to chlorofluorocarbons. Luckily, since this image was created, we've seen a rebound in the ozone layer, thanks in part due to a decrease in the output or emissions of chlorofluorocarbons. Above the stratosphere, we have the mesosphere. Like the troposphere, the mesosphere has temperatures decreasing with height. And we see this between 31 and 50 miles. We don't know a lot about the mesosphere. More recently, we've discovered noctilucent clouds, which are quite rare because we don't usually see water vapor creating clouds in this layer. So we have a lot more research to do in order to understand this layer and noctilucent clouds. Now at the top of our atmosphere, the major layer that we see is the thermosphere. At this layer, we're above so much of the atmosphere that we don't really have anything to protect us from the sun's strongest radiation. So we see temperatures increasing with height as we get closer and closer to the sun and farther away from molecules and other aspects of the atmosphere that tend to protect things from the sun's strongest radiation. So things that we see in the atmosphere or in the thermosphere up here, we see meteors start to burn. We see the aurora borealis. We also see the International Space Station, and we see extremely warm temperatures. Temperatures up to 2200 degrees Fahrenheit. But keep in mind that the atmosphere is very thin up here. We have very few molecules up there. But whatever molecules are up there are getting heated by the sun's strong radiation up to 2200 degrees. In your book, you may see a slightly different image. And I brought this up here because it's similar in some ways, but one thing that's on this image that you don't see in the other image that I've been showing is another layer called the exosphere. Now this exosphere isn't really a layer, it's just the transition part or transition zone between our atmosphere and outer space. I want to go back for a minute and talk about other variable components of the atmosphere. We're going to talk about natural sources, anthropogenic or human-induced sources, and natural factors that can affect air pollution. In addition to stuff that humans are putting up into the atmosphere through pollution, cars, industry, urbanization, etc., there are lots of other natural factors. Volcanic eruptions can spew lots of different particulates, ash, and gases such as sulfur oxides. Forest fires can induce a lot of carbon monoxide and also ash itself, particulates. If you have allergies, you're very aware that plants can produce pollens. Decaying plants can produce methane. Dust storms or soil they don't just put dust in the atmosphere, but they also include viruses. An ocean has a lot of salt spray, which can actually damage electronics in cars if you live near the beach. A little bit more commonly found around here as a natural source are wildfires. And when we have wildfires, especially a wildfire outbreak, we can get some nasty pollution. These are typically a natural source though. If we have a strong Santa Ana wind, which blows a lot of this pollution out at sea, then air quality in and around the ocean can be severely affected. One common thing that we see in the summer, and LA is known for this, is smog. But more specifically, we see photochemical smog. So as we have cars and industry outputting a lot of carbon monoxide, volatile organic compounds, nitrogen dioxide, that sits there in a bowl. Because remember, we have mountains that surround the northern and eastern side of the Los Angeles basin, and even more so in the San Fernando Valley. During the hot summer days, we have a lot of ultraviolet radiation. Not a lot, I should say, but some of it does make it down to the surface, mixes in with these gases, and creates this brownish haze known as photochemical smog.